My name is Abhisek, and in this video I will be demonstrating our tool called MoleculeMiner. This system has three main stages through which any PDF document as a patent or a publication in the chemical domain can be processed. The processing involves extraction of drawn molecule figures as well as linking them with important associated metadata such as its IUPAC name or the chemical name, its chemical reactivity, yield, etc. These are often found mentioned in tables either containing the molecule itself or anywhere in the PDF. So this is the landing page of our system. This can be run locally by anyone using their own compute. We open source our web app as well as our core codebase for extraction and parsing, including training data and models. Users will have the opportunity to run and process their own chemical PDFs. This page allows us to upload our chosen PDF to process and optionally also provide their own open API key for extracting metadata from tables. So over here you can see the users can choose their own PDF file. In this field they can specify an open API key if they have one. It's worth noting, however, that without the open API key, the system would still be able to perform basic extraction and parsing, and the users would be able to see basic molecule information such as the page number, the model confidence, and the parse miles corresponding to each detected molecule anywhere in the PDF. On clicking the Process PDF button over here, the system will run the extraction and parsing pipeline, and the results would be available in the View Existing Files tab. So, on clicking this tab, you can see that for the purposes of this demo, we have already pre-processed 3 different PDF files. So on clicking any of these files, let's say we click the first file here, you can see that the system allows us to basically look at all the pages where a molecule has been detected. So this is the first page where a molecule has been detected in the PDF. This is the second, and this is the third. So if we click one of these boxes, which are clickable, we can see its associated metadata as well as molecules properties. So for example, this is page 1 of the PDF with its smile string, which is important as a chemical property for a molecule to represent it in a 1D string, as well as how confident the model is in predicting the said smiles. You can see here that it's about 89% confident that the smiles that it has predicted for this molecule is correct. It also produces the associated metadata, which has been extracted from the table extraction stage to show the IUPAC name of this specific molecule. So once a user is done with this specific molecule, they can close this pop-up menu using the close button and click on some other molecule of interest. For instance, the compound 4 in this case. So they can get the same information as above. One important thing I would like to point out is that the metadata for any molecule does not need to be in the same page or in the vicinity of where the diagram is drawn. And I will demonstrate this now using my second test PDF. So in this test PDF, you can see that there are same molecules drawn in the PDF, but on clicking them, you can see that it has the information as the previous PDF, but it has an extra metadata table which is also visible here, and you don't see it inside the main PDF page where the molecule has been detected. So where does this come from? So on opening the main PDF, the original source, you can see that in the first page it doesn't have that information, but there is the second page here where you can see that on example 2 and 3, the inhibition constant, or Ki, in micromolar is 0.03 and 0.013. So if we go back to our table for 2 and 3, so you can see that this inhibition constant has been successfully extracted and parsed and linked to the molecule, in this case with the specific molecule in question. And this has been found from a different page in the same PDF and has been successfully linked. We do this, as we say more clearly in the paper as well, using the reference number linking. So the table that I showed before had its own reference number that has been linked with the reference number of the molecule here. The other feature I wanted to say or demonstrate was about our improvements to the specific MoleScribe version that we are using and have improved upon it. So one of the things you can see here is the detected boxes do not completely cover the molecule and sometimes leave certain parts of it out. So for example, in this compound 2, you can see that the edges of the H in the OH group has been cut out. So we improve upon the previous MoleScribe by including figures in the training set where these have been used in the data augmentation stage. Apart from that, other improvements also included having a better data set and improving the training set size from 1 million to 4 million, as well as our own contribution with the novel positional embedding technique in our SWIN transformer encoder. Okay, so as we near the end of this presentation, I would just like to thank my co-author, Nate Stanley, as well as some of my colleagues at In Sitro, where I worked as an intern, specifically Patrick Conrad, Benson, and Srinivasan. Thank you for your time and patience, and this is the end of the presentation. Thank you.